Good afternoon, everyone. I'm Lijuan Cui, a PhD student from University of Oklahoma. And the project I'm working on is about privacy-preserving data compression. And my project mentor is Xiaotian Jiang. This joint work with Shuang Wang, Samuel Cheng, Lucila Machado. The goal of this project is to provide practical solutions for secure privacy-preserving medical image compression. Here we call our framework SUPERMICRO. For the outline of today's presentation, first I will start with a quick review about the background. It's about the security and the efficiency of medical image sharing system, then followed by our proposed SUPERMICRO framework. Finally, I will discuss some future work. Now let's consider a medical image sharing system, where a data owner has a bunch of CT sequences and would like to share with multiple users. And each user have different region of interest. Here we call ROI for short. For example, user 1 may prefer ROI1 for performing ROI-based annotation, whereas user 2 would like to choose ROI2 for the researches or diagnosis purposes. Please note that here, data owner does not know the preference of each user beforehand, so cannot pre-assign the ROI before loading the data to the cloud. Since CT sequences contains a significant sensitive and private information of the patient, so it is extremely important to send these medical images in a secure way, as well as limited the access of each user within his or her desired ROI only. To achieve this goal, one worked around to send the encrypted image and partial decryption key. That's a key which can only decrypt the ROI of the entire slice, separately to the remote cloud and authorized user, such that each user could download the entire CT sequences from the cloud, but can only access the ROI from his received partial decryption key. This setup solved the security problem of ROI-based medical image sharing system. However, as the image data can be huge in size, so disseminating this uncompressed data are quite inefficient and would lead to significant communication burdens for both data owners and users. To tackle this difficulty, we need a technique that can compress the data even after encryption, so that both secrecy and efficiency can be achieved. However, it turns out that this problem is non-trivial, explained in the following. The key idea of the cryptography is to impose randomness to data, such that encrypted data appears statistically random. For example, as shown in the figures on the right, the values of pixels within the same slice before encryption has strong intercorrelation. However, after encryption, all the pixel values are roughly equally distributed. The randomness is necessary for security, but extremely undesirable for compression in a traditional science. It is because the principle of traditional compression is to remove the redundancy through exploring the structure of the data, whereas the correlation and the redundancy among pixels after encryption will be totally destroyed, which raises a big challenge for compression on encrypted data. To solve the challenge of compression on encrypted data, we propose a SUPERMICRO encoder based on the distributed source coding principle. The compression of encrypted bits is mainly based on the idea of the random coding used in the communication theory. For example, to compress the encrypted slice with size h by w, we multiply it with a tall binary matrix B with size w by m. So the output will be much smaller in size with only hm elements. Note that the distributed source coding guarantees the good compression even when the encoder has no statistical knowledge of the encrypted image. As shown in this slide, a user can decompress the I slice with the received compressed slice, the compression matrix, and a piece of the sign information that contains the knowledge of the I slice. This information can be obtained, for example, from the previously decompressed I-1 slice. This decompression problem can be modeled at inference problem and can be solved, for example, by applying the amplification algorithm on the graphical models. In essence, the proposed SUPERMICRO framework shifts the task of exploring the inter-slice correlation at the encoder to the task of exploring inter-slice redundancy at the decoder. We can see that even though a user may decompose the entire data, the decompressed data is still encrypted except the ROI where he had the respective key. Now, I will walk you through our experimental result. Our experiments are based on 2 different CT image sites with 100 slices in each site, for a total of 200 slices used. We can see that there are significant changes from the first to the last slice in each site, which offers diverse conditions for verifying the robustness of our proposed SUPERMICRO framework. Now, we will analyze the compression performance in terms of code rate for 3 different setups: the proposed SUPERMICRO framework on the encrypted slices, the state-of-the-art JPEG 2000 lossless compression on the original slices, and the same JPEG 2000 compression on the encrypted slices. Here we define the code rate at the size of compressed slice over the size of original slice, where a smaller code rate refers to the better compression performance. Here, the black dashed dot line showed the required code rate for JPEG 2000 on the original slices. This serves as the baseline performance to show how well slice could be compressed without any encryption. And the right dotted line shows here the required code rate of JPEG 2000 on the encrypted slices. And we can see that the size of the compressed data actually increased as the code rate are larger than 1. This offers some intuition of how difficult to compress encrypted data with traditional techniques. However, the performance of our proposed SUPERMICRO framework on the encrypted slices is very close to the baseline performance. This demonstrated that the proposed SUPERMICRO framework offers a practical solution for compressing encrypted CT sequences. In summary, we propose a secure privacy-preserving medical image compression, which guarantees the secrecy and the efficiency of the medical image sharing system. And for future work, we will continue to improve the compression performance by incorporating the correlation estimation algorithms. And in this summer, we submitted 2 conference papers and 2 journal papers in preparation. And finally, I will thank to my mentor, all the collaborators, and DBMI, and thank Kelly too, and thank NIH for following support of iDASH summer intern programs. Thank you.